Welcome to part 2 of the Convolutional Neural Network lecture. So in this part we will be looking at one-dimensional convolutions, and specifically we will be trying to build an intuition for them. So the example which we will be using throughout the slides here is an example of a sound wave, and a sound wave is basically one-dimensional. And what we're going to try to do is to use deep learning for answering certain hard questions about sound. So for example, given a certain sound wave, like the one on the slide, what is the style of this music, right? Or you would ask, does the user like this music, yes or no? And what you basically want to build there is a classifier, right? So this is a classification problem. You're giving a piece of music. Now tell me in which class it belongs. The second type of tasks would be more regression tasks, and that's, for example, what is the beat of this music? Right? So what is the underlying beat of, or the rhythm of the music, let's say. And secondly, it could be a question like, how pleasant is this music to listen to on a scale from 1 to 100? So besides these tasks, which are just the standard classification and regression tasks, we also have tasks which are considered even harder, right? And these are more generative tasks. So, for example, you get a sound wave, and the question which you're asked is, what does a cleaned version of this audio signal look like? Or you get a question, what audio would fit to these lyrics? Or you get a question, how would this song continue given a small part of the song? So these approaches do not just give you a class or give you an integer, or sorry, a floating point number. Rather, they would also, as an answer, produce you a sound wave. Okay, so traditionally, to solve this kind of problems, manual feature extraction was used. So you would basically design a digital or normal signal processing filter and apply that on the sound wave. This could be used, for example, for detecting the beat or for finding certain manually crafted patterns. Now, the problem with these things is that there are some problems, right? So one of them is, for example, noise. So if you have a noisy signal, these things don't work as well as they should. Then you have things like, for example, variations in the sound. Imagine you have a certain song which is sang by a male or by female. You might get a very different sound. Other things is, for example, you could have sound in which fragments are missing, and there these filters would not perform as well. Now, in general, the issue is basically that the type of features which you have to extract from the sound is not known beforehand. So you just sort of don't know what you should be extracting. Now, in a deep learning system, we want the model itself to take care of that feature extraction. Right? So the model is just going to do it, and you just feed it the raw data. So what we're still going, so let's first try to use an MLP for this, right? So we have been using MLPs before for other data, so let's try to do this, and we're going to do a classification task where we identify the music style. So what would we do in principle, or what we would do normally, is we would have these neurons. We would feed the information basically from the input into this input layer. Then we would have the weights on the connections between these neurons. Then we would have inner layers in which we basically collect the incoming information, sum it together and apply nonlinearity. And that way things propagate into the network. I did not explicitly mention the bias nodes in this image, but they are there, right? So in all the images which we are showing about MLPs, there's always also a bias node in these formulas and in the images. After things have forward propagated through the network, you can also use then backpropagation basically to improve the classification accuracy of that network. Now, of course, these weights which are here, we can just represent them with one big weight matrix. Now, as we already mentioned, so in theory, this might just work. But there are several problems, right? So one is that you need a lot of training data for this. The MLP does not look at the ordering of the inputs, as we already mentioned. And the last point we also already mentioned. So you would need a very, very large MLP, right? Because you need as many connections basically to neurons as you have input features, which would now be really, really a lot. And finally, this will basically not converge. Now, let's discuss a bit about our input data. So what a sound wave basically is a superposition of sine waves, right? So you have, that is basically what such a sinus consists of. And in reality, that signal, so sound wave, is continuous, right? So it's a continuous wave. But what we do for getting this into a computer is sampling it. So we're sampling it, for example, at a rate of 44 kilohertz is very common. And this makes it possible to store it digitally on a computer. So for a computer, a sound wave is just a sequence of numbers, right? So it is not a wave anymore, it's just a sequence of numbers. And for the sake of this lecture, we will just directly use this wave as the feature. Okay, so what we have is basically a one-dimensional vector of numbers. Now, let's look at how we can do that. So basically we have that sound wave. Now if we zoom in, we basically see that the sound wave consists of certain heights, let's say, or certain, let's say, y-axis values. And we can basically sample them, say like how high is this peak, and measure it and then put it into the vector. Now, what we will do what we will do next, basically, to use this wave, we will represent it slightly different. So the only thing which we will do is basically measure the amplitude of the sound wave, right? So we just say how loud is the noise in principle. Now, note that this is a rather reasonable thing to do, because if you have an MLP, in principle, you can already, with what you know, design an MLP which is able to convert that one form into the other, right? So it can take the original sound wave and just measure its amplitude, which is the same as computing the absolute value of the sound wave. So it might actually be a good idea to now pause this video and think for yourself how you can actually convert that original sound wave to just its amplitude. And the reason I really want you to stop the video is that if you're able to do this, you will understand much better what happens next in this lecture. Yeah, really stop that video. Okay, so in the slides you will find a possible solution for this problem of computing this amplitude from the original sound wave. Now, the next thing which we will be doing is we will take that amplitude and we will normalize it, right? So we will basically move it such that the values are between +1 and -1, and that the average will be around 0, or will be 0. Okay, so once that is done, we basically have our vector input. Now, for sound input, as we discussed already before, more in general, but also specifically for a sound input, the features in the sound wave are not independent of each other. So obviously, it's very important what the feature right before is and what is next, and this ordering is extremely important. So that also means that nearby features are more important as far away ones, right? So if you have, let's say, a certain sound, it's very important how that sound locally looks. It's also important what happens, let's say, 20 seconds later in the sound. And this idea that this nearby information is somehow more important as other things can be used in what is called a filter. And so what we will be doing with filters is we will first look into an example in which we try to find silence in our sound. All right, and so a silence, what does that basically mean in our case? Well, it is basically a period of time in which the amplitude is very low, or is close to 0, or exactly 0 during that time. And so what that actually means, so if we look at this example further, is that we have that period of time, so this period here, and if we look at the numbers, so the samples which have been taken from that original signal, you'll see that there is a period here where, where you basically have very low numbers for a certain amount of time. And that is basically what we want to be able to detect. So what we can try to do, and what we will now do, is basically we will try to create what I call a silence neuron. And a silence neuron is basically a neuron in the neural network which is responsible for finding a silence. Okay? So let's just kind of try to see what this should look like. Right? So we have, I've now just created a neuron here, right? So just your normal neuron, as I've seen before. Now the thing what I've done special is that I've linked this neuron up only to specifically these three inputs, right? So I've not looked at the previous ones, not at the ones after it, but only these three. And now what we basically want to have is that if there is a silence, which here is the case, then we want this output to have a high value, right? We want to have a strong signal in case this is a silence. Now, the thing is that if we want to get a high value there, then the sum of these parts needs to have a high value, right? And I mean the sum of the parts here in this summation. So we know that the nonlinearity is a monotonic function, right? So basically, to make that value high, you need to have a high value of this summation. Now, the input to this neuron to this neural network is already fixed, right? So that comes just from the input. And so basically what we can adapt now is the weights. And now the thing is that we want to have a large sum here. So we basically want to have high values coming in. And the only way to do that is basically to make these weights very low. Okay, so basically we have two negative numbers, so this will become a large positive number. And so this is sort of interesting. So we have a signal coming in, right? So these numbers coming in, and we can basically know what kind of values we need as weights in order to make this a high output value to have our signal. So the interesting thing which we now observe is that these weights which we have here, so these are all -1s, they basically have the same pattern, or at least a very similar pattern to the pattern we are interested in. Right, so in this case, we are interested in a silence, and a silence means a very, very low value. And what we observe is that our weights here also have low values. Right. So the point here is that when the pattern of your weights, so this pattern here of these weights, is similar to your data, you basically get a very high dot product here. Right. So that means that once your weights express the thing you're interested in, then this neuron will fire. Okay, and this kind of patterns, we call them filters, or sometimes also kernels, and this is a term which is directly borrowed from signal processing. Now, we will be doing a bit of changes to represent this more compactly. So the first thing which we will do is we will represent our filter as a vector. Right, so instead of having this representation as a graph, we will have it as a vector, which is very similar to what you have already seen by representing things as matrices or tensors. Okay. Now let's clean up even more. So because we have a lot of stuff there which we don't need, and what we will basically be left is something like this. So we have our input values, and I just put my filter right next to it. And what you have to imagine is that this means that there is a small MLP just connected to these input neurons, I would say, that there is a bias, that there is all the connections, and basically things can be computed. And now what we can do is in this case, we can compute actually the output of this neuron, which we have here. And that output is going to be basically just multiplying these values with each other and then summing up to get that sum. Then we still apply that nonlinearity. I left basically open what that nonlinearity can be, but you can basically have any kind of nonlinearity here. Now, a question which we still have to answer is whether this noise filter, as we called it, the silence filter rather, whether this really works. And what I mean by that is really working means it's now giving a high value, but what it should also do is giving a low value in case there is no silence. And so let's just try whether this works, right? So we start at the top of the sound, and what we notice here, we get a value of 1.2. So it is already a lot lower as what we just saw before. Now, if we sort of slide down, right? So we go one step further, and we apply the same neural network on this at this spot, our sum will become 1.6, right? So it's still a reasonably low value. And then we see here that the closer we get to that silence, the higher the value becomes. So here we get the highest value which we will obtain. And then after this period of silence, the number will start decreasing again. So there are several observations which we need to make. Right? So we are trying to just detect that there was a silence. We applied that filter and then we see what happens. So the interesting thing, or the first interesting thing, is we know now that this filter can act as a feature extractor, right? So we can use it to detect, in this case, silence, but we can also have other, or you can imagine other configuration of the filter where you extract other kinds of features. The second thing which we observe is that this filter cannot just be used on the one location where we were first looking, but it can be used to detect silence at any position in your data, right? What we did as an example is sort of sliding that filter over the data, and this operation of sliding a filter is called convolving, or it's called, and this whole operation is called convolution operator. Now, the other thing which we already saw, but which I didn't make explicit, is that the output of this convolution operator is again going to be a vector, right? So we had that input, or we had that input here on the left. We could apply that filter basically on these three values. We got that value. We got the next three values. We got that value, and this output can again be represented as a vector. And another thing which we observe already here is that if your sound signal here would be shifted, let's say that you shifted by 1 second, right? So you move all the values just down, then also your output will shift down by the same amount, right? And what we say here is that convolution is a translation equivariant operation. So it means if you do a translation in the input, you will get exactly the same translation in the output. You shift this one 1 second, the other one will also shift with 1 second. And we will come back to this feature of convolutions later. The next thing is, when we are continuing our discussion on this convolution operator, is to always keep in the back of your mind that this convolution operator is just a small MLP, right? And it's a small MLP that just wanders across the input signal. So it goes all around your input signal and then gets applied in different positions. We also already, you know MLPs, right? And we already mentioned this, but in practice, these convolutional kernels, so these weights or these filters, they are learned, right? So you have already seen backpropagation, and essentially that is also the technique which is used for learning these filters. What we will be doing next in the B part of this part 2 is to go into more theoretical details on the convolutions.